There's a lot of activity around cybersecurity for land vehicle electronics, and we're going to kind of give an overview of the landscape, where things are. Um, First thing with I can't advance here. There we go. If you want to connect with me, I'm on LinkedIn. You can connect with me. I post videos there and things as when I first post a video before it even hits YouTube, sometimes I post it there, and then I hand it off to Arpin to put it on our YouTube page. So you might get some, pretty up-to-date videos that I did. And most recent video I did was on DDS, which isn't the topic today, but we might touch on it. So today, mainly talk about cybersecurity. And the first thing, when any cybersecurity whatsoever, the first step is to really analyze what's the motivation, what are you protecting against? That's the first thing you have to think about. What are the motivations? And really come up with a strategy on what are the possible, what we call attack vectors for any type of cybersecurity. It really boils down to what's the motivation for someone to try to do something malicious to what you're trying to protect. So you really have to start with motivations. And really, vehicle hacking has been around for a very long time. If you can think of, even modern vehicles, of course, there's lots of electronics that could be hacked. But even in the old days, before there was very much electronics in the vehicle other than spark plugs, vehicles were hacked in a way that OEMs don't want them to be hacked. In other words, increasing power, changing carburetors. These are things. This is one form of hacking that motivates a lot of activity in cybersecurity, in the sense of OEMs create a vehicle and they have their warranty around that vehicle. They don't want someone that purchases the vehicle modifying the vehicle, and because it could affect the cost back to the OEM, specifically on warranty related things. So I'm in the community. I know people that do off-roading or whatever, and they can some people that I know, they modify a production vehicle, and if it breaks, they have to modify it back to original condition, give it back to the dealer, and it really does drive in warranty costs. So that's one major motivation. There are many others, especially with electronics these days. It gets a lot more interesting, because now that we have vehicles connected to the internet, the worst case scenario is that someone is able to figure out how to connect to a vehicle remotely and control the vehicle remotely. Now we're talking about serious threats to safety. So that's a big motivation these days as well, just because there's a lot of fear around it. And if you look under the hood, we're going to talk a lot about really what the potential for controlling vehicles remotely really is. But if you're not in the industry, it sounds scary. All the vehicles are controlled by electronics and they're connected by the internet. Therefore, someone can log into 1,000 vehicles and control them remotely. It's not really realistic. But of course, back in 2015, someone was able to hack a Jeep and affect the way it was controlled remotely, which means theoretically it could have been done to lots of vehicles. So really, my understanding of this one was that it was effectively hacking the parking assist functionality, which, of course, it's sensationalized. This hack is sensationalized as if it was, a huge threat. There could be a million vehicles out there, and all of a sudden, someone pushed a button and they can control the vehicle remotely. Not entirely true. So, for example, there was one video where I was able to disable the braking in the vehicle, and that particular one was, an activating parking assist. And the one thing about parking assist is OEMs, they realize that could be a big threat. So, for example, they disable it below, above 5 miles per hour, a lot of OEMs. So there are a lot of built-in cybersecurity safety measures that aren't even really communications related. We're going to be getting into cybersecurity related to communications in vehicles. That's the main part of this presentation. But really, from a holistic approach, it has to be looked at. What are the simplest ways of preventing threats? And for example, if you have park assist, you don't need to be parking a vehicle if you're going to 50 miles an hour. So one easy way of preventing, one easy way of protecting one attack vector would be, okay, make sure that the vehicle doesn't go into that mode and can't be controlled if it's, going above 5 miles per hour, for example. So a lot of the safety related capabilities in the vehicle aren't necessarily, directly trying to prevent hackers from getting into a vehicle from an electronic or communication standpoint, but just making smart decisions about how to design the vehicle in the first place, such that we don't activate unnecessary safety critical features in a condition in which it could be dangerous, for example. So that's kind of the introduction. First thing with cybersecurity, that it's not as exciting. It sounds kind of boring, but really you have to know who, what's the motivations and who and wants to attack the vehicle and for what reason. So, and then we're going to build safeguards against those reasons, against those attack vectors, and when we design the vehicle. And some of those safety measures aren't all always necessarily, I'm going to implement some kind of new algorithm from a cybersecurity standpoint. It could be just, I'm going to design the vehicle so it doesn't get into the condition where it can be dangerous. So, and today, most vehicles that are being designed for markets like the US, Europe, and such, we're moving into a world where all OEMs want to be software companies, right? They want their stock prices raised. So then software defined vehicle, they want they want to be software companies. So this is a big motivation for OEMs to have software defined vehicles. Effectively, what it means is just vehicles that are going to be more flexible after production can be, software can be updated. You get more features that are related to services on the vehicle after they're sold, like maintenance and other things. Even BMW tried selling like services. It didn't succeed, but I think they had some new feature around heating. I think it was the heating and cooling system on the seats or something, and they tried to get a monthly subscription on that, which didn't succeed. But things like that, where they're trying to add features and improve the vehicle after production. So SDV vehicles, if we look at underneath, what does it mean? What we've had for the last 30 years or so, and is what we call domain-based architecture. That is, you have a subsystem of the vehicle, like a powertrain, braking system, and a certain domain. I mean, this domain is responsible for some functionality of the vehicle. Let's take braking, for example. So large OEMs, they'll just buy the whole system from some supplier, Bosch or whoever, some big supplier. They'll buy the whole they'll buy the brakes, the whole braking system, the mechanics, and the electronics from the supplier. And they'll do the same thing for HVAC or like heating and cooling. They'll just buy the whole system from some big supplier that can supply the whole system, including the electronics. And then another, subsystem might be lighting in the vehicle. Another subsystem could be, different comfort features in the seats in the vehicle, door locks, windows. We all know all the electronics that's in the vehicle. So what's happened kind of evolutionary wise over time is we have a network that's dedicated to a particular functionality, like a CAN network dedicated predominantly to powertrain, another CAN network for braking, another one for lighting, another one for door locks. And so what's happened over time is we've designed vehicle networks for particular functionality, a subset of functionality that the car needs in these domain architectures. And the end result is if you've got one CAN network here, another CAN network, we're laying networks on top of networks. And it's not always CAN. I say CAN because it's the most popular control area network, but like in a lot of European cars, FlexRay is still really popular. We still have LIN out there. So whatever networks it happens to be, there tends to be numerous networks, and end result is that we've got wiring running from the back to the front of the vehicle for lighting, wiring running from the back to the end for HVAC, wiring going for braking, and it's all effectively redundant wiring in the sense that It's multiple networks being run with multiple different wires from the front and the back of the vehicle, and the end result is we have a large number of electronic control units in the vehicles, lots of number of microcontrollers with little smart devices everywhere all around the vehicle that are distributed. It's basically distributed computing with domain type architecture. And then in order for different domains to talk to each other, you have to have gateways. Gateways is sort of a complex device that enables communication across different domains, subdomains within the vehicle. These gateways have to be high powered because you have to do real-time communication translations from one network to the next. Sometimes the network technology is different, like for FlexRay to CAN or Ethernet to CAN and vice versa, LIN and such. So bottom line is electronics in the vehicle has become extremely complex and it has become the most expensive and also least it tends to produce the most problems as well in the field. So as a result of, we're going to find out as a result of newer technologies that we now have, which we're going to talk about a lot, is automotive Ethernet specifically. As a result of new technology, specifically automotive Ethernet, we now have the ability to carry a lot more bandwidth of data than we ever could with other older legacy networks like CAN, FlexRay. CAN and FlexRay, upper limits, you can make arguments where the upper limit is with each one, but let's just say around 20 megabits per second. And so there's lots of data on networks that we have to transfer in the vehicle that's more than that. So what's happened is again, one network doesn't do it, and therefore you split the network in two, and now you got two networks, and that's kind of what's happened evolutionary wise. But then about 10 years ago or 15 years ago, automotive Ethernet was introduced, and it started off with 100 megabit Ethernet. 100 megabit Ethernet, is already 100 times faster, or really 200 times faster than what we typically would see with a controller area network. We're running at 500 kilobits per second. And then from there, we can go even faster, gigabit Ethernet, and we have multi-gig Ethernet. We have customers now that have up to 10G in their vehicles for various applications. So now we have a lot of bandwidth. So what that means is we can rethink how we do networks in the vehicle, and really the term's called zonal architecture. So if zonal architecture is synonymous with SDV. Zonal architecture is sort of the engineering term for what SDV means. SDV is more like a marketing term. So when we talk about zonal architecture, what does it mean? It means zonal architecture, some words that are synonymous in the automotive industry. Zonal architecture, SDV, central computing. These are kind of synonymous. So in this paradigm, we're going to throw away the idea that we're taking all these subsystems and it's the networks is in the old world, networks were designed, the ECUs on the network were all created based on the functionality that it's going to provide. That's the domain. In a zonal architecture, we're going to organize ECUs and networks not based on the functionality that the electronics provides, but rather where in the vehicle does this thing need to be located. That's why we get the name zone. Zone means an area, so it's really, we're going to connect the ECUs and actuators and sensors, not based on their functionality that they provide, but rather where are they located in the vehicle. And what this does is it effectively enables you to group within a smaller region, multiple functionalities or domains together, and then have a reduced number of communication paths back to what we call central computing device or high-powered computer, high-power compute module. And we're going to have network communications between all the different parts of the vehicle. There's going to be multiple domains supported on the same network. And then we're going to have one central computer that makes as many decisions as possible, eliminating the need for the intelligence in every ECU. So what this does is, at a high level, and this isn't the focus of the presentation, I'm just kind of laying the groundwork for, when we talk about cybersecurity for SDV, things are much different than cybersecurity for other types because the network architecture is fundamentally different. So I'm just laying the groundwork for why the network architecture is fundamentally different. It's because we got now a central compute module that makes as many decisions as possible. And the devices then that are actually doing the control in the vehicle, turning on the lights, opening the doors, unlocking the locks, doing the heating and cooling, even a lot of the functionality around the vehicle then is now controlled by one computer, not a networked group of computers. And that provides a good platform for being able to update vehicle software easier. You're messing with one ECU now rather than 20 from 5 different suppliers. So that's the other issue is if we want to change the functionality of the vehicle after it's been released, it's really a tough call with the domain architecture because you might have 20 different ECUs around some functionality from 5 different suppliers, and you got to coordinate all the source code changes and everything else. So putting everything in one piece of hardware simplifies that a lot. And so now we're messing with one piece of hardware, but it also simplifies the number of wires that we have to connect between the ECUs, and additionally reduces the number of individual electronic control units that we have to have in the vehicle. So the projections, the numbers that I've seen are something like 30% reduction in cost for wiring harnesses because you need less connectors, you need less wiring. Roughly the same number of reduction in number of ECUs or electronic control units in the vehicle. If 30% is actually a small number, might be larger than that. So really where we've seen, like a modern vehicle, like a big SUV from, luxury manufacturer, you're going to have over 100 different electronic control units in that vehicle. In the future, with SDV type of design, you might see that, reduced by 50%. You might see 50 ECUs where we're putting as much intelligence as possible in the central processing unit and removing the decision-making capabilities from the individual ECUs. So that's another way to look at it is another way to visual or to think about SDV or zonal architecture specifically is where in the past we've had numerous ECUs with lots of different microcontrollers coordinating like distributed activity and distributed control. We're putting that in the central processor. So we're taking that intelligence, what used to be spread across the vehicle, multiple ECUs, as much as possible, putting it in one. What this also does is effectively we're reducing the complexity of the wiring, the hardware, the connectors, the number of ECUs. We're making a big push to reduce the weight, but what's the end result of this effort is the communications that has to happen between these devices is much more complex. Because in the past, an ECU would make a decision, I'm going to unlock this door. It would unlock the door directly. Now, the decision is made by the central compute module, and the central compute has to remotely control that actuator. So there is a lot more remote control over the network happening in an SDV vehicle. And SDV vehicle, its ultimate goal is to have everything controlled from one central unit. Everything is remote control over a network. So naturally, if we're going to control things over the network, it means the network communications has to be very reliable, and we're putting more burden on the network itself than we did in the past. And so we're trading off complexity of the electronics hardware, wiring, ECUs, and the trade-off is we're increasing the complexity of the computer, the communication protocols. And we're also expanding our attack surface for cybersecurity. We're making it larger. You can think about it that way too. So the more that we control remotely over the network, the more that we're exposing for someone else to come in and hack and then control those same things over the network. So it's pretty safe to say. With SDV, attack surfaces for remote, because we're doing remote control, become larger. The one thing I'll say, I don't have we don't have all day just to talk about SDV. We got to get into cybersecurity. But most SDV platforms we're not messing with safety critical stuff. So like anything safety critical now, practically speaking, braking, advanced driver assistance systems, autonomous driving, those stay a separate entity just because it's too much to go to a new architecture and then put everything safety critical on top of that same architecture. It's not a good idea. So really the first step with SDV, which is where we're at now, it's mostly non-safety critical features that are built on top of the network. I'm just saying that as a caveat. But this is kind of what it looks like. Enablers for SDV to even happen, central computing, is, as I said, automotive Ethernet, because we get the bandwidth now that we need to be able to do this, which we didn't have before. But also there's tons and tons of protocols that happen that enable this type of control too. So if we're going to do real-time control, first things first, you got to have time alignment, right? You have to, if you're going to communicate something remotely over the network, the ECU doing the control and the actuator better be thinking about the same time frame. And so time synchronization, time becomes important. That's GPTP, Generalized Precision Time Protocol. Gives you time, accurate time synchronization across the entire vehicle, less than 1 microsecond. So that's good. We got transport layers, IEEE 1722. This is a fundamental component of remote control, where you can have data structured in a way that you can send out an Ethernet message, but inside that Ethernet message is data that can control like I2C, SPI bus, or CAN bus, or physical I/O. So we get these remote control protocols now that control physical things in the vehicle, and that's also something that we've designed in the vehicles. And TSN, time sensitive networking. This gives us the ability to tightly control things on the network, deliver things within a time budget, so we can tightly control latencies of communications. And also for safety critical applications, we can have redundancy. So we can send out one message and it actually gets split into 2 different messages, redundant paths. So that's all safety critical capabilities. So what we're talking about today is mainly security. You can see here that now that we have central computing, basically every central computing type vehicle, its backbone is always going to be Ethernet, and the Ethernet communication between the central compute and all the other parts of the vehicle is built on Ethernet and built with these fundamental protocols, which means our attack surfaces are much larger than they used to be. Attack vectors for vehicles, of course, the most vulnerable attack surfaces are the ones that interact with consumer electronics of any type, like an OBD port, any Wi-Fi, Bluetooth, all these things where we can connect to vehicles via the internet or our smart devices are going to be attack surfaces. So we have to pay special attention to those. The unfortunate thing with vehicle networking and with Ethernet in general, Ethernet's built on a layered approach to communications, where at the lowest level you have a physical level, and then at layer 2 we have a MAC frames, and the MAC frames then carry data. And if we're talking about TSN communications, that all happens at layer 2, we say with MAC frames. But then if we get into other types of communication like some IP, DDS, those live on top of UDP, I'm sorry, or some types of IP communication. So that's like the internet communication that's on, of course, for the internet. So that means basically anything that can be hacked in the internet can be hacked in the vehicle with these types of things. This whole slide is to show, I don't have time to go into every detail, but because of the layered approach to vehicle networking, or Ethernet in general, not just vehicle networking, but Ethernet in general, the unfortunate thing is every single layer is its own attack surface. So even if you protect at one layer, let's say layer 2, doesn't mean that you're going to protect other layers. So it's a very easy example is imagine that you have perfect security at layer 2. We're going to talk about MACsec, MAC security. That's layer 2 security. It's really good. It's nearly impossible to hack. But let's say that someone is able to download a malicious application into your ECU, right? Is MACsec going to help you there? So let's think about it. So the malicious application can generate a message inside the ECU. That message then is going to get wrapped in standard MAC frames, So if you get hacked up here with an application, and that application wants to send something, the lower layers are just going to treat that as normal data. Like it's okay, it's just fine. So if you got hacked up here and you have perfect cybersecurity at layer 2, it's not going to help you. That layer 2 cybersecurity is going to treat that data as normal, perfect, average data because it doesn't know about the upper layers. That's the whole point of having the layers. So layer 2 doesn't know about layer 7. So the layer approach to networking with Ethernet specifically that we've done always forever with internet communications and such, it provides disadvantages when we're talking about cybersecurity because, again, you can get hacked at one layer and cybersecurity at a different layer is not going to help you at all. Not even going to know about it. That's the point of the layers. Like layer 2 doesn't know about layer 7. So we have to look at a holistic approach. So we're going to see as we go through this, there's no one technology that's going to solve this, make your vehicle cyber secure, let's say. There's no one technology that's going to do that. You have to take a holistic approach. Like I said, big part of it is design features that make sense. Don't allow your parking assist to be functional above 5 miles per hour. That's a very simple. It doesn't even nothing to do with the network. Those are the smartest things to do. And when we get into network communications, we're going to talk about a few different technologies at different layers because that's where it's important. The only other thing I want to say in general about cybersecurity is that the algorithms that we have for cybersecurity in automotive are really identical to the ones that are used outside of automotive. So mathematics behind everything, we don't have time to go into the mathematics, although it's very interesting. I love math. Everything's done for you already. If you have a hashing algorithm, there's 256-bit, SHAs and all types of 128 or 256, especially when you talk about 256-bit based algorithms. Those are mathematically proven to be basically unhackable. I say that with confidence. I know it sounds maybe arrogant or with some hubris, but literally in order to reverse engineer a 256-bit algorithm would take like a supercomputer, the length of like 18 billion years, something like that. So in the past, there were like with 64-bit encryption and lower, you could actually brute force reverse engineer the algorithm itself just by looking at data. But some of the principles that we have now that really provide really good protection if it's done right is you always use 128 or 256-bit algorithms for hashing, for encryption, decryption, and such. There's many different standard ones out there. There's a handful of very popular ones. There's the same ones that are used in automotive as outside of automotive. Some of the same protocols we're going to use in automotive as outside of automotive, like TLS, for example, that's very popular outside and inside. That's pretty much the standard type of communication cybersecurity for all internet communications. And it is unhackable for a couple different reasons. One is the algorithm itself is 256-bit, which is would take too long to reverse engineer just brute force. And then secondly, the other thing that we're going to do with most algorithms, we're going to have ephemeral keys. We're going to have temporary keys. So what that means is we're going to constantly refresh the keys over time so that even if you did lose a key, someone figured out a key, someone read it or whatever, it's only going to be used for a temporary period of time. So that really provides the best protection against hacking. And anything that we do now, TLS, a lot of, MACsec, for example, uses MKA, MACsec key agreement, where we do ephemeral keys. That's almost impossible to hack. Even if you do hack it, even if you do get a key, sorry, it's only going to be good for 10 seconds or whatever it is. You're not going to be able to do anything with that. So we'll talk about cybersecurity, a few of the fundamentals. There's always a key exchange of some type. Depending upon the, with TLS, we have this what's called Diffie-Hellman key exchange. We'll get into that, but it's a way you can do a key exchange and not have to do much handshaking. You can reduce the amount of back and forth that you have to do. So TLS 1.3 requires Diffie-Hellman. But in any case, you have to have some type of key exchange. Keys are the fundamental part. Keys are the weakest link as well. It's not the key itself that's the weakest link, because if you're using 256-bit key, like I said, it can be hacked. But someone's got to know that number. Some human somewhere has got to generate that number. That's your weak link. Boom. How do you, that human, whoever, those people that have to manage those keys, that's your weak link. How do you save it? Who gets access to it? Who gets to generate keys? Who doesn't get to generate keys? That's the fundamental hard part of all cybersecurity is key management. So authentication, most of what we're going to do in automotive industry is authentication. So authentication just means that a receiver can be guaranteed that the transmitter is a good and valid transmitter and not a malicious, not from a malicious source. That's all authentication means. We're not trying to hide. So whenever we start, if someone's not familiar with cybersecurity, often authentication and encryption gets confused. Encryption means I'm going to actually try to hide the data itself, which is important for a lot of things. If you're doing a financial transaction, you don't want to have someone else find out about your data. But for many things that we do in real-time control, we're talking about automotive land systems. A lot of what we do in the electronics of the vehicle is real-time control. So with real-time control, let's say you're driving down the car and someone's able to see your vehicle network traffic, and they can read engine speed or your vehicle speed. Okay, so what? What can they do with that data? Who cares? Let them read it. Like, it's engine speed. You got that on your display, right? On your tachometer or vehicle speed. So a lot of the signals and data that we transfer in real-time control, and this is not just true for automotive, but for any type of real-time control system, don't care if someone reads it. They're not going to be able to do anything. There's not identifying anybody's financial information, So the real thing is use cybersecurity as least, the technology to secure things. Use the least amount that's necessary, not more. You don't want to encrypt the entire network because that makes everything more difficult. And there's no such thing as a free lunch when it comes to cybersecurity, right? So if we're going to do authentication, it's going to cost something. It's going to cost processing power. It's going to cost time. If you're going to do encryption, guess what? It's a lot more time and a lot more processing power. You can't have encryption and not introduce a delay in latency on the communications path. It's impossible because you have to calculate, whenever you're doing encryption, you have to do some type of bulk manipulation with a cipher suite, and that takes time. And you have to have the data up front. So when we're doing real-time control, we're just, generally shipping stuff out as quick as possible, and there's not a lot of data, there's not a lot of history of data there. So to do encryption on that, costs us. So you only want bulk encryption when it's necessary. If you're doing a file download and it's the software file for your ECU, probably a good idea to do encryption on that because you don't want someone to be able to see the plain text of that and be able to reverse engineer anything from that. So, in the vehicle, software downloads, software packages, anything with user information, of course, we're going to encrypt that, but we don't need to encrypt most of the things like real-time communication, like engine speeds and temperatures and all that stuff. It's just, it's not necessary. And then there's hashing algorithms I always use. Hash is just a way of taking a large set of data and being able to uniquely identify it with a smaller number. So we just take this large number, reduce it down to a smaller number, and being able to uniquely identify that block of data with this smaller number. That's effectively hashing. Okay. There's naming conventions. So whenever we talk about different algorithms, you can, TLS is the protocol, key exchange. Everything's going to be Diffie-Hellman now. This one's the ECDHE stands for electrical curve, Diffie-Hellman exchange. I'm sorry, not electrical, elliptical curve. So a lot of algorithms have used in modern cybersecurity. It has to do with ellipses. Mathematics turns out to be ellipses. So Diffie-Hellman key exchange is very important. We'll talk about that with TLS. And then what authentication method you're going to use. If you're going to do encryption, what's the encryption algorithm? And then what are you going to use for hashing? So there's kind of a loose standard around how to name different cipher suites. So whenever you have two computers need to communicate to each other over some type of cybersecurity, the first thing that has to be agreed upon is what's the cipher suites we're going to be using. And of course, for engineered vehicles, you only need one and it needs to be agreed upon. You can hard code it. But like if you're communicating with your laptop or your Linux system if the car needs to talk like from the Linux system to some server somewhere, that server may not support, you might want to have several options that are popular because in the communication, the first thing that has to happen when you connect and you want to connect securely with TLS, for example, you have to decide what cipher suite you're going to use. And both parties have to support the cipher suites. Okay, so I already mentioned hashing. Takes a long number, produces a fixed length, and you can uniquely identify that number. There's some things about cybersecurity in general that the math needs to do very, very well. One thing is like a good, for example, algorithm, whether it's hashing or whether it's encryption or whatever else. If you change the input data even one bit, right? If you change it one bit, you want that hash to be modified a lot, right? And so that's like kind of avalanche effect. So like if you change, if a hacker is just trying to change one bit to figure out your algorithm, the output changes so much, it's so dramatic, it's not going to provide any value to them. So that's one thing in the mathematics. Of course, we want determinism, meaning the same input always producing the same output. We want it to be fast computation as possible. Everything we do here costs money in terms of computation power. And what's that translate into cost in automotive space? It translates into miles per gallon because it takes more energy. And the energy the electronics uses is real. It's something that we really have to calculate. Yep. Collision resistance, no two inputs should produce the same number output. So those are some of the fundamentals when we're talking about any type of cybersecurity algorithm. Now here's the big ones that are out there today for cybersecurity for automotive. SecOC is just a generic way of protecting any type of data with any type of network. So you can use SecOC on, it's just a description from AutoZar. So it's defined in AutoZar, designed for automotive communications. It's just a way of saying, okay, I got this piece of data, I want to authenticate it or optionally encrypt it. And how do I do that? And it's just one piece of data. It's like small pieces of data. So this goes back to like automotive in the sense in the old days, it was pretty much all just sensor data, small packets of information, engine speed, trans speed. So SecOC is still used and I expect it to be used long-term in the future. It gives you the ability to say, okay, these parameters I need to protect. These other ones I don't care about. I'm not going to use SecOC. So it's sort of like you selectively use SecOC for just the parameters that you're interested in, just the piece of data that you're interested in protecting. And that's the right way to do it. It's useful for nearly any type of network. It's very common for CAN, FlexRay, and can also be used for Ethernet. It is dominant in the way it is popular for like some IP payloads as well, just because it's easy to use SecOC sometimes it's called with any type of communication. And so I've seen this used by OEMs in some IP payloads. TLS and DTLS, this is definitely the most popular type of communication protection mechanism on the planet of Earth, just because this is what all internet transactions are protected with. The older form of it's called SSL. You might hear SSL in the past, but that's the SSL is secured socket layer means you're using an old version of TLS. So really any modern browser requires TLS 1.2. 1.3 is the latest. And so 1.3 gives, every iteration we get improved handshaking. And 1.3 requires like Diffie-Hellman key exchange, which means you you can just have one transaction and exchange keys just by sending data rather than what's your key, and it's kind of encoded in the communication path itself. We'll talk a little bit about that in a second. And then we have IPsec. IPsec really is designed for Internet Protocol security. That's what it is. But IPsec is used predominantly in the world for one purpose, and that is VPNs. So if you're using a VPN, the fundamental technology is IPsec. That's what it was designed for. In automotive, IPsec is, I have seen it used, but I think it's a bad choice no matter what you do. The reason why it's a bad choice, it only works on IP communications, doesn't work on other non-IP communications, just like TLS, DTLS. TLS is for TCP and DTLS is for UDP. So TLS and DTLS only work for TCP or UDP. And likewise, IPsec only works for IP communications, which means effectively UDP and TCP. But not in the real-time control world, outside of automotive and other real-time control industries. It's basically everything that we do on the internet is TCP or UDP communication. So that it does well for that. But TLS, DTLS, we're going to use in automotive, but we're going to use it only with, can only be used with TCP or UDP. IPsec, the same thing. And IPsec really was designed, it's still used today for VPNs. VPNs is the technology is IPsec for VPNs. And then the one thing that we are going to use in automotive is called MACsec. MACsec is the lowest layer type of security, layer 2, and we're going to try to go through each of these. Keep in mind, though, that TLS, IPsec, and MACsec are only Ethernet. So really, the only one you're going to use that's kind of universal is SecOC. That's popular. You can make your own cybersecurity too, but I'm just talking about the standard ones. And as far as I know, OEMs are just using the standard ones. I'm not worried about anything that's not standard. We're always going to try to use something standard than use something not standard. So let's talk about cybersecurity, a little bit more fundamental concepts. There's two ways, type of communication protection. There's one thing called end-to-end or app-to-app, and that's the best type of communication. Now, let's just say we need one application to talk to another application in different ECU. And let's say these two applications share a key. What we can do is we can use TLS and DTLS to perfectly protect that entire communication path, all the way up and down. Because we're doing the cybersecurity at the high layer, it means if we do this right here, we will detect any modification in any of the lower layers. So that works really well. But here's the problem. It's only point to point. So that means this communication and this communication need to share a key. Now, if you needed this app to talk to this app, you need a different path. And if you need a different type of data, a different socket, different port, a different IP address, every single IP address, every single port, every single path needs its own key shares. So it gets completely unmanageable very quickly. It's order, it's a number to the order nth of the number of connections that you need. And it'll completely gets too complicated really quick. This is the reason why we can't do app-to-app cybersecurity for everything. Another reason is TLS and DTLS. They're not designed for real-time control either. So like timeouts and how fast does it take communication? How fast, how much latency are you introducing by introducing TLS and DTLS? They're out of the bounds of what we can accept in automotive real-time control. So really, you're not going to be using TLS or DTLS typically for real-time communication unless you really are planning on using some sophisticated hardware and doing some extra engineering to ensure latencies and delivery of the data is going to be in a timely fashion. None of that was designed in TLS or DTLS because it's not needed for internet communication. You just kind of assume you always have enough buffer space, enough time. If your YouTube information arrives at your computer 250 milliseconds late, no big deal. You're not going to notice that, but you're going to notice it in the vehicle if you're doing braking control, right? So that's the other thing. These provide very good security, but not as good real-time characteristics. Here's what we do with MACsec. It's called point-to-point. MACsec, basically, you share keys between one PHY and another PHY. So this is point-to-point. And you're only protecting this layer so that someone can't come in here and disturb the communication here. And the other thing that it protects of is someone taking away the ECU, replacing it with a malicious ECU, because they're not going to have this key. So MACsec has become popular. It's become popular because it protects the network really well at layer 2. It protects really well from hackers being able to replace an ECU with a different ECU that you don't want them to. So those are the main man-in-the-middle attacks, and replacing ECUs, that type of thing is what we protect with MACsec, and that's a big concern. So. So every type of, I'm almost out of time, so I'm gonna try to be quick here. Almost every type of communication, almost every type of cybersecurity works with this, where you have to have some secret key, okay? And the secret key, I don't know if I'm getting into asymmetric versus symmetric. If you have the same key on both the sender and receiver, it's called symmetric encryption. And that means one key encrypts and the same key decrypts. So that's the fastest way to do encryption and decryption or authentication. And when we talk about authentication, we can use the same key to do encryption, decryption, and also authentication. But effectively, almost all types of cybersecurity work with these fundamental premises here. So if you understand this slide, you'll understand most of everything we're going to do with any type of communication. That is, you start with some key, that's just some number. It's just a number. That's a secret number, and that's going to be input into an algorithm. And here I got AES, CMAC, but it could be all algorithms have the same inputs. The data that you're going to want to protect goes in as well. There has to be some random number or counter. The random number or counter prevents replay attacks. It's always necessary to prevent against replay attack. Without a random number or counter, you could just record data and then replay it back on the network at a future date. And without that random counter or timer, something, you're going to have a problem in that the system will accept the data. But if you have a random counter that the system knows in real time, that random counter is not going to be valid in the future. Therefore, it protects against replay attacks. So you're always going to have some kind of initial vector, random counter, depending upon what algorithm you're using. And then out of this algorithm for authentication, you're going to have an integrity check value, ICV, or sometimes called. There's also a message authentication code, MAC, which is terrible if you're talking about Ethernet because it has nothing to do with the MAC address of Ethernet. So don't confuse the two. But like in SecOC, it was designed, and they call the ICV, they call it MAC, which is a completely, utterly, the dumbest name you could probably ever imagine, because that's what a MAC address is. You don't want to confuse the MAC address with the message authentication code. But sometimes this is called, I always use the term ICV, not to confuse it with the MAC address. But a lot of algorithms like SecOC call it the MAC, the message authentication code. So all this is we're sending the data with the ICV, and then on the receiving side, it has the same algorithm. It needs to know the initial vector. There's some mechanism that has to be dealt with here so that the receiver can know what the vector or the random number that the sender is using. But let's leave that aside for now. Of course, you're going to have the data, and in this case, we're just doing authentication. So the data is plain text. You can read it. I don't care. I don't care that anybody sees what the data is. I just want to be damn sure that this data is transmitted by a valid source. That's all I care about. And you know it's transmitted by a valid source if you know the key used in that calculation of the ICV is a valid key. And you know that because the receiver has the secret key as well. And so it takes the data, it knows ICV, it has its own secret key. And if the data is the same, the vector here is the same, the key is the same, guess what? ICV is going to be the same too. Right? You're putting into the same algorithm, the same inputs, and guess what? In mathematics, we get the same output. It's pretty simple. That's all it is. And as long as you keep the key secret, it's 100% valid. Like no one else is going to know that key. And so anybody else that tries to transmit anything with an ICV, it's going to be an invalid number because they don't have that key. We're assuming they don't have the key. If you let the keys get out of your house, you're totally effed. Forget it. You're screwed. So the most important thing is making sure nobody could read the keys. So how do we do that? In automotive, we do that through like most microcontrollers will have a key storage part of the chip where you write it and no one can read it ever again. You can write it once and not even you can read it again. The only thing you can do is clear it. That's it. So once and there's also external chips that do the same thing. There's external chips for automotive specifically that, you program the key one time, you can never read the key. You can use the key, but you can never read. No one can ever know the key value, not even you. So that's pretty common with all electronics these days. You can only erase the key. And most chips will automatically generate keys as well. So it'll generate the key, store it locally, and then you have to. It's a little complicated how the keys have to happen because you have to program the same key. If you're using symmetric encryption, you need the same key on both sides. So that's what we're using for real-time communication. The keys are need to be secure. They need to be secret. Talk about. Hopefully, we'll have time. And if you want to encrypt the data, it's just an extra step. These algorithms will also take the data and they'll output the same size vector, same number of bytes, but just modified so that you can't see what the original data was. So if you want encryption, is just a second optional step of authentication, really. That makes sense. And the same thing, if you got secure data, the algorithm can just unencrypt that and you get the plain text out. So encryption is just an optional step. But again, for most SecOC stuff, you're concerned about authentication, not encryption. We'll only use encryption sparingly. So that's how SecOC works. Basically, I'm running out of time. But basically, you have an AutoSAR, what's called iPDU. There's a header that identifies the PDU. Then you have the actual data you want to secure, and then we actually transmit. It's optional, but we can transmit the freshness value, and then the MAC, again message authentication code, not MAC address. And there's some tricks being made here so that we only use partial of the data. I don't have detail to go into all the details of this. I don't have time to go into all the detail. But SecOC does exactly what I just said with some extra little tricks to make it more efficient for automotive communications because we're talking about really small amounts of data. The freshness value, some of the tricks that we use, as I said before, the freshness value has to be shared on both sides. Both the sender and receiver have to know that. And so what does happen is when one boots or another boots or one goes away and one comes back, what often happens is, and also in SecOC, the receiver can keep a table of recent freshness values. And even if you miss a freshness value, the algorithms will be, try this one, and if this one doesn't work, try 5 more. And then after 5 more, if it doesn't work, then just throw away the data. It's not good. So that's kind of like, we play a lot of little games here with the freshness values because the sender needs to send it to the receiver and it needs to be matched to the data. But again, without going into every level of detail, there's lots of sort of massaging of the protocols here. This is where the protocols will be different. SecOC will say you have to do this with the freshness values, and let's see, MACsec doesn't have that. Okay, so which is a point. This is sort of the freshness value is important in SecOC, but there's a way that we can avoid this whole scenario, and that's what TLS and that's what MACsec does. And it goes back to what I said before, ephemeral keys. So what happens in that world, well, I think we're getting into MACsec next, so let's just go there. Let's talk about TLS. So let's get into that's kind of the the fundamentals of how SecOC works and the fundamentals of how all cybersecurity works. But we haven't talked much about the keys which we're going to have to talk more as we get into the more modern types of cybersecurity like TLS and MACsec. So as I mentioned before, TLS and DTLS, it either works on TLS is TCP only, DTLS is UDP only. There's always a TCP handshake that always happens anyways. And then essentially what happens right after you get a TCP communication with an IP address and a port, you get connected on TCP. The very next thing that's going to happen with TLS is a handshake as well. It is quite complicated, but there's a client hello, and the client hello will basically tell the server what its capabilities are. And in that same data, it'll actually do a key exchange as well with what's called Diffie-Hellman mathematics, which we don't have time to go in today. But effectively, what's important to understand is after the TCP handshake with TLS, you get a client hello and a server hello. And once the client sends its information, the server sends its information. So the client sends its information. It says, okay, these are the cipher suites I support. And session ID uniquely identifies this communication path. There's a random number sent, and what TLS version. So a bunch of information. The server then will decide from the list of client supported cipher suites. The server has to support one of those, or else we cannot communicate securely. But if the server does support one of them, it'll choose the one that's the strongest. And then in the server hello, it'll come back and also there's a key exchange that happens here. And then the server and the client, after just two passes of communication, have keys that they can use, but they don't use the keys directly. So another thing we can do with key, any key, so it's key again, it's just a number, like a 256 bit number. We can generate new keys. So what happens in TLS and MACsec is you don't use the key from the server directly. You generate a new key, and the server generates a new key that's the same key with the same algorithm. And what does this do? This protects the key. Like you don't even transmit the key that you're using. The key that you're using actually to do the communication is never transmitted on the network ever. So that protects the communication right there alone. Like the key's only ever in internal memory on the server and the client side. So you're using these what's called ephemeral keys. It means ephemeral keys are just effectively you're taking some golden key that doesn't change, and you're going to generate ephemeral or temporary keys from that key, and both sides are going to do that such that you never have to communicate the actual key value yourself. The main key has to be transmitted, and that main key will get encrypted. Of course, there'll be encryption for the key, the main key that's transmitted. But once the communication starts, once you start getting bulk secure data being communicated, you're not even using the main key. You're using the ephemeral keys. And the ephemeral keys, they're called ephemeral because they'll time out, and you have to do a new key exchange. So let's say it depends on like in MACsec, you might do a new key exchange every 30 seconds or something. That way, every 30 seconds, you create new keys and you're using new keys. And so even if someone were to reverse engineer one of the ephemeral keys, it only is valid for a short period of time. So it's super strong communication protection. And that's what we do with MACsec as well. So I'm going to try to get through some of these. MACsec, first of all, this is the most popular broad use cybersecurity in automotive. Some OEMs are like, we're going to use MACsec in every Ethernet frame on the vehicle. If you're going to use MACsec, it's easy to use it for every Ethernet frame because once you get it working, it's very easy to make it work for every frame. And it works on layer 2. It works on layer 2. First thing is, the only way to really make this work is if the computation is done in the PHY itself, in the chip, in the Ethernet chip. Because if we're going to be making cybersecurity calculations on real-time communication, you're talking about gigabit Ethernet, that's going to be 100% of your processor right there. Boom. Your processor's not going to be able to handle that computation, period. So first thing with MACsec is the only way to practically use it is if it's built in the computation for MACsec built into the PHY. So you have to buy Ethernet chips that specifically support this. Basically, anything for automotive is going to have support for MACsec. So the PHY itself will have a built-in MACsec engine where you just supply configuration information and a key, and it does the rest of the computations. So you don't have to actually know the computations. It's built into the hardware. So here's the overall architecture for MACsec and MKA. There's two things. MACsec's actually pretty simple. It's just like we said, just like SecOC, right? It's just going to do a calculation of the data that it receives, do an ICV, and the receiver is going to check the ICV with its own locally calculated ICV to see if data incoming is valid or not, right? It's pretty simple. That's what MACsec is. The hard part about MACsec is in order to use ephemeral keys, you have to have a MACsec key agreement. MACsec key agreement is a bit more complicated. So MACsec key agreement, this is kind of an overview. You do have a host. You need to have some kind of key server. There needs to be some device out there that's going to serve keys to the whole system. And basically, you have a stored key called SAK, or no, shoot, what's the stored key called? It's called the
association key.
No, that's the ephemeral key. My terminology is losing me here. There is another key. I forgot the name of it. Sorry for the acronym. I can't remember. There is like a golden key that's stored, and from which all other keys are generated. And the key server has that. There are several keys used in MACsec key agreement. There's a key for it's called the KEK key encryption key. That's the key that encrypts the keys that you're going to send ephemeral keys. Everything's generated from one key though. And the key, there needs to be a single smart device with like a microcontroller that does the sending of the keys. And then so you have I think I have this somewhere. Yeah, I'll get to that in a second, but since I'm out of time, so this would be like the PHY, the actual chip that does the communications. This is the receiver PHY, and then the host. Effectively, what the host has to do is send in. It has to send the key into the PHY as they're being changed. So as the ephemeral keys are being received from the key server, your microcontroller has to send those keys into the PHY itself, where these are ephemeral, and then because they're ephemeral, and we're going to be exchanging keys, the PHY has to be able to handle more than one key at a time as well, because you might have one key using an older key, or one device using an older key, a slightly older key, and it still needs to handle communication. So you need to have like an overlap. So you'll have with MACsec, just like with TLS, during a short period of time, you might have more than one key active. So because they're ephemeral, you put in a new key, the transmitter starts using the new key, but the receiver, you have to make sure that the receiver has a new key before you start using the new key. So there's a communication that has to happen between receiver and sender, and saying the receiver says, okay, I'm ready for the new key now. And then once the receiver says it's got the new key, the sender then can use the new key. And then until then, the sender has to use the old key. So during key exchange and ephemeral update, the sender and receiver may have two active keys. And so this is an 802. This is an Ethernet frame, basically where you have a destination MAC address, source MAC address, a VLAN tag, payload. All this is the same as everything in blue is just an Ethernet frame. What we're doing with MACsec is we're going to introduce a new ether type for MACsec and basically insert a sec tag. So we're increasing the actual frame by 16 to 32 bytes. And then the integrity check value is effectively what I said before. So if you look at the ICV and the payload, it's identical to what I said before, really, with the SecOC. It's no different. So this and the payload, everything's the same, where you have some integrity check value, and that integrity check value is a combination of some random number, the data that you want to authenticate or encrypt, that means the rest of the data in the frame. That's another input. And then the third input, the fundamental one, is the key that you're using. That would be the ephemeral key. So that's going to give you your ICV. And then the sec tag just provides additional information for things like you might have more than one channel using between two devices. You can have multiple channels of communication. So effectively, what this does is it enables the senders and receivers to uniquely identify multiple communications of data. So that's just sec tag information that's required. That's either 8 or 16 bits. We were not going to get into all of this, of course. So I'm running out of time. Yeah, so here's what I was trying to describe earlier with MKA. So with MKA, like I said, you have to have some key server. The server typically is in whatever switch you're going to have. So the switch is going to be like you're going to have a switch in the central processing unit. So often the central processing unit's the key server. And the way it works is effectively the key server generates multiple keys from it's called the CAK. That's the main one. That's generally stored in like an HSM, like a hardware security module, very secure. So you have to have a CAK, and that CAK is sort of like your golden key. Then you have a key derivation function. The key derivation function will generate 3 different keys. The integrity check key, that's your key that you're going to use for the integrity check calculations. Key exchange key, we're going to encrypt the keys with this KEK as we sent the ephemeral keys. And then the SAK is, also the one that's used real-time communication, getting into the PHY. So effectively what's important here is one key server generates keys and has to get transmitted across the network. Every ECU that supports MKA or MACsec has to be able to receive this information and then program the PHYs with these ephemeral keys as they're coming in. So some OEMs are like, oh my gosh, this is a lot of complication. And it is kind of complicated if you think about it. Like MACsec itself is as fundamental as SecOC. It's pretty simple. You take a key as an input, take some data, calculate the integrity check value, send it on, and the receiver does that. But as soon as you want to start using ephemeral keys, which is the best protection, which is required for MACsec, I guess it's not required. You don't have to use MKA without MACsec, but it's kind of like a cake without icing. You know, I mean, what gives MACsec its security and its resilience against hacking is the fact that you're using ephemeral keys. And in order to get that, you have to have MKA, and MKA is what really complicates things a lot, unfortunately. So there are OEMs that don't use MACsec at all. They just use SecOC. There are other OEMs saying I need MACsec on every communication whatsoever. So it really depends what you're doing with the vehicle and your opinion about how important it is. You know, especially the Germans, they really don't want anybody hacking the vehicle, like adding on additional functionality after it's been sold. So they tend to use the MACsec and the MKA for all communication. I could spend a whole hour on MKA and all this stuff, but obviously I don't have time. We got to close it down. So in conclusion, fundamentally, SDV is, you're going to have to employ some cybersecurity methods with SDV. There's just too many attack surfaces. It's too dangerous. You're doing remote control over network communications. It would be not a good idea to not employ a good cybersecurity, strategy for SDV. So any SDV vehicle is going to have high level of cybersecurity, but the cybersecurity is going to be selective. For example, your OBD port, your Wi-Fi port, any Ethernet communications that happens directly with the vehicle, you're going to want that to be secure communication, of course. But that's, you're going to want to selectively use TLS for that. When you do a software download, for example, you don't care if the file arrives 10 milliseconds later or earlier. It's not that important. What is important is that it arrives exactly as it was sent, and no one can see what was sent. So you're going to want to use encryption for software download. But you can't use that type of cybersecurity for real-time communication because you have variant latencies and how long it takes to encrypt data, right? Especially with TLS and certain algorithms, you don't know how long it takes up front, how to calculate, certain things. And so any encryption or authentication is going to introduce latencies. So if we have real-time communication, that is between, all of this here, some OEMs say, okay, I'm going to protect all of the real-time communication with MACsec. And with MACsec, you can have bounded latencies. If you're just doing authentication, you know exactly what the latencies are going to be introducing are, and they're within ranges of error that you can handle. And so a lot of companies use MACsec for just all communication that's real time. These is where the focus needs to be. You have to have TLS or real good strong encryption there. And I know of one OEM that was planning on using IPsec, but to me, I think it's a complete mistake because important with automotive communications is a lot of automotive communications it's not happening on top of IP. And so you need some type of protection. Like if you're doing real-time safety critical stuff, you're going to probably be using TSN, time sensitive networking. None of that is IP, none of it. So if you want protection outside of IP, which I shouldn't say a lot. The most safety critical and real-time communication that happens on top of Ethernet in the vehicles with TSN, and all TSN is not IP. So using protection methods that only work on IP doesn't cover all of the attack vectors that you could for automotive because we're doing real-time control. So some use MACsec. Some here we can also use SecOC. As long as you choose an algorithm that's 128-bit or higher, you can be assured that it's not reversible. You can't brute force attack that. That's true for any cipher suite that's 128, 256-bit that's modern. So that's kind of what OEMs do. For sure, using TLS for communication, software downloads, diagnostics. Selectively use SecOC on real-time communications for the parameters that are important to be protected. Or use MACsec for all layer 2 security. And if you use MACsec for all layer 2, you can rest assured that nobody after the vehicle's sold is going to be able to update the vehicle with electronics that's not approved by the manufacturer. So I think that's really where the decision between some OEMs to use MACsec or not MACsec is. Some OEMs aren't as concerned about, having devices that are not manufactured by the OEM as part of the communication after the vehicle's released. You can still protect it with SecOC. But you'd have to selectively make sure there's SecOC used for every device in the vehicle. Whereas if you use MACsec, everything's protected no matter what. Hopefully that gives an overview on cybersecurity for SDV.